electric field strength versus distance, how would the graph look like? Okay, so once more, last class I went through it quickly. Share করতেছি দাঁড়াও. Yes, I know. It should be there. Yeah. Okay, so what is the first one here? The first one is electric field strength versus distance, and all these graphs are electric field strength versus distance, but for different types of objects out there. So the first one is uniformly distributed charge. So what does that mean to begin with? So it means that you have this sphere here where the charges are evenly spread out. Okay, so that's what it means. So charges evenly distributed. What's the consequence of that? So the consequence of that is that whenever you take a small piece of this material from any place, how much charge will you have in it? The same amount. Okay, so that's what uniformly distributed means. So in this kind of a material, if you go from the center to the surface and then beyond, how does the graph look like? So before we get into the inside part, let's just clarify something, that the graph for the field outside the sphere is always going to be the same. And the reason behind that is beyond the charge, the equation for electric field strength is the same for every kind of charge out there, as long as it's like a sphere, okay, or a point. So this E equals to KQ by D square gives you this graph. So you'll find that they're all the same in all of them, right? But the difference comes what's inside. So if it's a uniformly distributed charge, what does that mean? It means that there are layers of material stacked upon each other that have charges on them, right? So that would mean that as you start to go from the center outwards, what is building up? The amount of charge. And as the amount of charge builds up, the amount of strength also builds up, right? So what you see here is a straight line that goes up like that. And this kind of a straight line here indicates that the charge is increasing uniformly. Now, let's say this was not a uniformly distributed sphere, right? The graph inside would be random. It depends on where the charges would be, okay? But because it's uniformly distributed, that's how the graph looks like, all right? And then it goes down. Now, the next thing that we learned was what would it look like in a hollow metal sphere? So hollow metal sphere, there's this unique thing going on here. The inside is shielded from the outside, which means that in the inside, you can't have any electric field. Okay, so the electric field is not basically doing anything on the inside. So in the inside, you have no electric field. So you see it's flat zero there. And then suddenly, if you reach the surface, you have all the charges on the surface, right? So that means the field strength is the highest on the surface, and it decreases again. Now, the last one is metal sphere that's charged. So if you have a metal sphere that has charges on them, let's say electrons. Electrons are easy to understand. The electrons are everywhere like that. And you let them move around freely, okay? So if you let the electrons move around freely, do you think that the electrons will stay where they are? Or would the electrons move around? They'll move around, right? They'll experience what from each other? Repulsion. And what will happen is that the electrons will all move to the surface. So whenever you have your metal sphere, the charges will always end up on the surface because they want to be as far apart as possible from one another, right? So eventually you'll find that the graph for this and that is the same. But the main thing, right, that we need to take away from here is that if my object had no dimension, right, how would the graph look like for all three of them? So there's no dimension out there, right? So let's say a dimensionless sphere, insulated sphere, a dimensionless hollow sphere, dimensionless solid sphere. What would the graph look like? Yeah, so they all will start from here and go like that, because since they don't have any dimension, we can't really say what's going on inside. So the graph will look the same on the outside. And that's the reason why we make a assumption. It's called the point charge approximation. What is that approximation? We assume that everything is a point. And what is the advantage of assuming everything to be a point? You can ignore what's inside because the inside doesn't really impact your calculation. So if I'm trying to figure out what kind of field this sphere will exert on me, I'm on the outside, right? Does it really matter what's inside? No, right? Because regardless of what kind of scenario you have inside, isn't the external field the same for all three of them? So that's why it's a justifiable assumption. The assumption that we assume that everything is like a point charge. Okay. Now, if you go into large scale, let's say there's actually a ball in front of you. in that case, these equations won't work because that ball is now appreciable in size. It will have different impact on you. Okay. So the electrons are inside the sphere or outside. So depends. So in this scenario, let's say this one doesn't have any, so this is net positive charge. So the electrons will move to the inside. So they'll be distributed on the inside like that equally. And let's say this is negatively charged. So there's more negative charges, so they'll move to the outside. So the excess charge will be always on the outside. Okay. Right. So this is what we did. I have added some notes here. I'll let you copy if you want. Did you copy the graphs last class? Yes. Oh, the shielding, right? So the shielding is the inside is hollow, right? And a hollow space should have a field, right? But the problem is that you have positive charge here, you have positive charge there, and let's say there's a charge on the inside, right? It is basically getting affected from all sides equally to create like no net effect. Yeah, they cancel out. So this is done in 2 places in your syllabus. This is one of them. And in future, we'll learn something called magnetic shielding. You can do it using iron. Iron will block the magnetic fields from entering the inside. Okay. No? Achha, okay, I'm telling shop graph actually did it, or you can copy whichever you want. So these are not that common, by the way. I don't recall last time I've seen them, but they have shown up probably in the last 5 years. This one, very common. Okay, this one is like every other year you'll find one of these. Okay, so what is this? This is the electric field strength versus distance between 2 unlike point charges. So how would the graph look like? So eta করার জন্য, I think we already discussed it. I'll go through this one more time. We use a point test charge. So this test charge idea is very useful in solving questions. What is it? So let's say you have this field out there, and you want to understand the effect of field at a point. So I'll make a simple example there, okay? Imagine the walls in these rooms, they're all charged, okay? And this remote that I have here, or sorry, this location I'm pointing at, isn't it like a space in the 3D space? What is the field strength here? This wall is positive, that wall is negative, that one is positive, the floor is negative. There are all different types of charges out there. And I want to know what's the net effect here, like that location there, okay? X, Y, Z coordinates. So there's some X, Y, Z value. Right. So what we do is we will take an imaginary charge and hold it here. Okay. And the imaginary charge is always going to be a what charge? Positive charge and a point charge. And then you see if this wall is positive and my charge is positive, what will it experience? Repulsion. That way. Then the wall at the top is negative, my charge is positive, what will it experience? Attraction. So eventually you'll find that there are 6 vectors acting on it. This way, that way, that way, that way, right? And then what do you do to the vectors? You combine them, and that's something we're going to do today. Okay, that's how you find the net electric field strength at a location. So what you do is you take a test point charge, and then you find all the forces individually, and then combine them using vector diagrams, parallelogram method, whatever method you like, components, right? So yeah, so what we do is we take a test charge here. This is very basic. There's a positive charge on this side, there's a negative charge there. So I'll place my positive test charge here and try to imagine how the forces be. And I will figure out that the repulsion here is going to be very large because you're right next to the charge, right? But the attraction from that negative charge out there is going to be what? Very small. It's a repulsion face করতেছে, এটা attraction দিচ্ছে না on my positive charge. My positive charge will face what from this positive charge? Repulsion. And my positive charge will face what from that negative charge? Attraction. Turns out both the vectors are pointing in one direction. Yeah, they'll add up, right? Vectors. So what will happen is you can think of it as a resultant arrow, this black arrow I'm going to draw right now. And as we start to go further away with our test charge, right? Let's say come here. Do you think that the resultant would be the same, or will it change? So it'll change, right? And it turns out it changes because the repulsion is now what than before? Less, because you're what from the charge? Further away. And the attraction is what compared to before? Little higher, right? Because you are closer to the other charge. So that's how it's going to be. But turns out the values are changing exponentially, which means that both of them have decreased, or both of them are quite low right now because they're very far away from both the charges. So if you look at the resultant here, you'll find the resultant is there, obviously, but it's quite what compared to the force before? Less. Yeah, it's going to be a little small, right? So it decreases. And we find that right at the midpoint, if they're identical charges, the value is the least. So you can think about the arrow here, but be very careful. It's going to be a non-zero low. Zero with the because there are two vectors pointing in the same direction, right? They can't be zero. So, but they're going to be the lowest at the center here. Once you cross the center, this thing starts to what itself again, replicate. But this time, who's responsible for the increase? The attraction, right? And the attraction will become very large as you go that way. So once you plot the graph, it looks like this. One very important takeaway from this graph is the fact that the graph is entirely what value at every place? Positive. What is that an indicator of? That the resultant net electric field strength is always acting in which direction? Same direction, right? Contrary to what students normally do, they'll feel like, oh, this is positive charge, so positive field. Oh, it's negative charge, so negative field. Maybe the graph looks like that. And there is actually a graph that looks like that, but that is not this graph. Okay, that's where the confusion arises. So just be careful that this graph is this here, and this thing that you see here, this is not the electric field strength of one charge. It is the what electric field strength? Net. Okay, net is the important part here. So since we are here, we'll wrap up our last graph from this topic. When a last graph from electric field strength, we have the same set of graph coming up later on with electric potential. So yeah, number 5, electric field strength between like charges. So how would the field strength look like between a pair of like charges? Let's see. So we'll follow the same process, and I want you to do the thinking here. So tell me কি করব এখানে. So আমরা এখানে positive Q. This is also positive Q. Let's say it's the same amount of positive Q as well. Right. So test starts a পাশে রাখলাম. This is gone. These are gone as well. So yeah, tell me what to do with the graph. Where do I start? How do I start? Which way does it go? Well, right next to this, right? Achha, okay. Before that, there's a question here. Why can't it be 0 at the center for the previous one? Right. So, tomar ki okay answer korte paro? Why can't it be 0? Yes. So try to imagine, in order to be 0 here, right? What should the strength of that have to be? 0. What should the strength of this also have to be? 0. I don't know if you realize, but E equals to K Q by D square. Mathematically, যদি 0 করতে চাও, right? Just using one charge, where do you need to be? No. মানে charger বাইরে, if I want my strength to become 0, where do I need to be? Yeah, at infinite, right? Because KQ by D square na, so when it's infinitely far away, then only E can be 0. So এখানে যদি 0 হইতে হয়, it is possible. It's just that both the charges are how far apart from each other, infinitely far away. They're so far away that as you start to move away from one charge, you've gone so far away that neither of the charges actually influence you anymore at the center, which would mean that they're the two edges of the universe, let's say. That it's maybe possible. Okay, so in our case, right, you will always have a value here, and it can go very close to 0, but can never be 0. Okay, because 0 korte like cancellation order, which is not happening here. Acha, anyways, let's try this one. Yes. Yeah, but in like charge it's done. So the right. So let's see what's happening here. So in this case, what will this do to this one? Rebel. But what will that do to this? Repel as well. And which direction? Yeah, opposite direction. So what will happen is there's going to be a net force here, and the net force is going to be little less than the actual repulsion because it's getting reduced slightly, right? And as you start to move closer, let's say here, here, we'll do at 3 different places or 4. Right. So can you tell me what will happen to the repulsion here? Decreases. What happens to the repulsion on the other side? Increases, right? Which means my resultant is now going to be getting lower. But interestingly, if you go right at the center, the repulsion of this will become exactly opposite to the repulsion of that. And when I mean exactly opposite, I numerically mean exactly opposite. So what should my net value be? 0, right? And then once you cross this thing, it replicates itself. এটা হচ্ছে আরো ছোট হতে থাকবে আর এই repulsionটা আরো বড় হতে থাকবে. Sorry. But you'll find something interesting happen right now. Can you tell me which way is the resultant now? The same direction or the other way? Yeah, because there's a 0 crossover. Once you cross that point, it becomes the other way, right? And as you go here, you'll eventually find that the resultant is acting which way? That way. So if I take all that information and put it into a graph, you start from a high value, right? What do you meet at the center? 0. And then once you cross that and go the other way, right? Do you go up or do you go down? Down. Why do you go down? Yeah, because it's a vector, it's negative, it's going to be the other direction. Okay, now can this graph be this?
Yes.
And this exact graph can be that, because again, a plus minus key mean for is subjective. What your plus is not probably my plus. Plus can be left or right. So the graph shape can be this or that. Don't worry about that. Okay, the main thing is it going from a plus to a minus, and is it crossing like a 0 at the center or not? All right. So yeah, these are all the graphs that we have from electric field strength versus distance. Are কিছু knife for the moment. So key question জিজ্ঞেস করে on the exam. One very common question would be, they'll give you this diagram here, like exactly this diagram, and they'll ask you, what are the charges? Are they like charges or unlike charges? It's a very common question, right? And we obviously know it's a like charge scenario here. How would you answer though? How would you convince the examiner that these are like charges? Yeah, one is that the main track here, students will go like, oh, this is positive, this is negative, so it must be unlike charges, right? But it is not. The thing is, they're like charges, even though this is a plus and this is a minus. So how do you word your answer to prove that this is still like charges here? One way. Yeah, you can say that. So you say that initially the net force acts one way, and then eventually the net force acts the other way. And this can only be possible if the forces change in direction, right? Resultant force. And that can only happen if you have what charges? Like charges. Is whatever they're doing this way, once you cross the 0, they're just doing that same thing the other way. Okay? So that's one way of doing it. Before I'll give you the notes and everything. Can you tell me what does the gradient of this graph give you? Gradient of this graph. Value of K. What does the gradient of this graph give you? Electric? You're actually right. It doesn't give you anything. It's basically E per meter, electric field strength per meter, which is not a unit that we have. What does the area of this graph give you? Charge. Area of this graph, voltage. Okay. No, voltage. Voltage came in with it. How do you figure that out? How do you figure its voltage? Huh? So electric field strength is V by D, right? And E into T would be V. Okay, so that's potential that's being represented by the area. Okay, so you don't need to know that. A graph actually is not a very useful graph out there, but আমাদের এরকম আরেকটা graph আসবে called the potential versus distance graph, and that has plenty of information. Okay, the field strength বের করতে পারবা, gradient you can find force. There are a lot of things you can do out there. So yeah, these are the graphs. I'll give you like notes on this, but before that, questions have some bolo. Do you have any confusion, anything that you need clarification with? Okay, copy girl. So the area and the gradient of the graph doesn't really give anything meaningful, so you can ignore it. But yeah, the area gives you potential V, which we'll see very soon. Dolce field strength. $103. So there's also math involved here. So proper, I'll give you the math. Like you have to find the null point of a setup. Null point is where there's no field strength.
The graph started from 0.05.
You have a question? So, no, so let me just clear myself. There's a graph out there. You have a line that you've drawn, and they're asking you to find the y-intercept. But the graph probably doesn't intersect with the y-axis on the graph you have drawn, right? That's
So do we actually use the equation y equals minus plus 0 to be
oh, so you the origin was shifted. The origin was not 0, 0. Achha, key point here. Which one was shifted? Both x-axis, y-axis, or just the x-axis? Huh?
only the y-axis?
No, then no problem. No, because the definition of y-intercept is when what is 0? X is 0. So as long as x is still starting from 0, the value is fine. If the x is shifted, then you can't do it from the graph. You have to use, you first have to find the gradient, then y equals mx plus c, and the c will be your answer. Because otherwise it's impossible, right? And then your A2, the graph is usually provided, like the values on the graph, right? So in that case, it was already given that x is shifted and y is shifted. Yeah, then you can't find intercept from the graph. It is just never possible.
So he gave an explanation that
Instead of calculate, that's fine. The only time you have to mandatory use a graph is if the question says using the graph find the gradient, or using the graph find the y-intercept. Determine means plot, fine. right? So however you find it. Yeah, it's a chain reaction because the problem with the graph questions that you get one thing wrong, that just becomes like five things wrong because if you so far I've seen that, man. I don't want to give you false hope. দিলে তো ভালো. Is the equation for electric field strength also applicable inside metal spheres? No, not possible. Inside metal sphere, you have to derive equations separately, assuming like there are surfaces from multiple directions and come up with an equation. So not possible. Not possible based on what we learned. Are you guys done with the first one? Okay, just disclaimer দিয়ে রাখি তোমাদেরকে দেখো এদিকে. This graph here, right? There's a version in some textbooks where I've seen it to be like this. এরকম দেখতে. Okay? This is what, by the way, do you remember? Metal charge sphere, right? So the reasoning that it's in your textbook, by the way, আমি তোমাদেরটা বুঝে আগে. তোমাদেরটার মধ্যে বলা যে হচ্ছে the charges will all move to the surface, and the key word here is all. Okay, all of them move to the surface. Why is that so? They're experiencing what from each other? Repulsion. And the inside doesn't have any more charges left. So the charges on the surface. But there's this hypothesis out there that what if there are way too many charges out there? And if there are way too many charges out there, this outside will become saturated. And they will start to repel charges which way? Back inside. And inside it, they'll create like a layer like that. And this layer will become saturated because there's too many charges out there. And that will push charges which way again? Further inside. And inside there is a case out there, and this is actually possible, where the inside becomes what charged? Uniformly distributed, even though it's a metal sphere, right? And it was originally just allowed to freely move around. It is going to happen under a very unique condition. It's called charge saturation. What's charge saturation? There's way too many charges out there that the surface can't hold charges anymore. So where do the charges then start to move? Inwards, right? So ওইটা দিয়ে একটা demonstration আছে. এটা I don't think like the UK syllabus follows it, but এটা হচ্ছে I found online এই simulation এর মধ্যে ওরা use করে. So this one is here. Just দেখাই রাখলাম এটা. I don't think এরকম controversial কিছু একটা ওরা দিবে তোমাদেরকে যে হঠাৎ করে চার্জ বেড়ে গেল, but this is a demonstration to explain charge distribution. So see what I'm going to do right now. Okay, I'll keep increasing my charges, and do you see how they move to the surface? And you see the whole surface is saturated, and the surface doesn't have any space for any charge to build up anymore. You see the surface is fully aligned with electrons. So the extra electrons, where will they be? Little inside, right? So if I keep doing this further, it's a charge saturation way. So it's just like all on the surface, right? So if I keep decreasing it, do you see what I explained is happening? Where are the charges now? Surface. Because the surface has enough space for charges to freely move around, right? So in this simulation, they consider this to be saturation level. It's a modeling depend. How do you model your surface? How do you model the capacity of your surface, right? আমরা তো square দিয়ে করি না, আমরা bar দিয়েও করি না, but just for understanding purpose, if a bar is fully saturated, right, this is how it looks like. What do we deal with? Sphere, right? So let's see what happens in a sphere. So it's a circle. So one random electron out there. Why is this just standing there? Yeah, it's just random. Right? Let's add one more. They try to go which way? As far apart as possible. The simulation is pretty accurate because mathematical model ওরা একদম কোথায় চলে যাবে? Two opposites, right? The diameter is the opposite. Do you see that the opposite ends of the sphere? Let's add two more. This will form 90-degree at setup, like like a crosser moton. See, if keep increasing, at a point in this model, they consider this to be like saturation. So do you see now the charges on the inside? And if I keep increasing them, this is now actually uniformly distributed inside, right? Do you see the distribution inside? It's uniformly distributed. So there is actually a mathematical reasoning behind this, where if you go beyond a certain value, the inside becomes uniformly distributed because it's experiencing equal force from everywhere and spreading out like that. So on this syllabus, we will stick to that. Okay, is that clear? If there are no charges in the middle, how do they have repulsion? They repel each other. Are you talking about when there are two charges? Yeah, one repels the other. শেষ? Do you guys have class after this?
Yes, sir.
No? So I want to do a math. So math kore gele bhalo. Class. I want to start potential next class. So potential is the end of electric field. Three. Shielding bullet. So the field lines don't cross each other. There's a requirement. The way the field is designed, like the lines can go through each other. So lines are coming out like that, right? Nothing can actually go inside. It's the same reason if you remember all levels in magnets, they didn't have any field lines inside them. All the field lines were outside. Acha, let's move on. So I'll give you time to do this. So যদি কারো class না থাকে after this, ওই time এটা copy করো if you want. Okay, I just want to do the math right now. It's important math. So math হচ্ছে like there's a 50% chance of a math or a graph in your exam, but there's a 100% chance of what? A question from here. Okay, so that's why you have to be clear about this topic. So this is interaction between. So there are two questions that we need to look into. Okay, so the first question is very basic. You have done something like this already. I just want to give you a reminder it's possible in this chapter as well. So you have this charge here, and a charge positively charged. Right, so positive charge here, and there's another positive charge on the other side. It's a charge plus 1.6 into 10 to the power minus 19 coulomb, which happens to be the charge of what? An electron or a proton. This is positively charged, so proton, right? And the distance between this charge and the other charge, which is on the other side, is 1 meter. And the other charge is also a positive charge, okay? So center of charge, take a center of charge, which is distance or provide course. But this one is plus 3.2 into 10 to the power minus 19 coulomb, double the charge, okay? And turns out between these two charges, right, lies a what region? Null region. Why is that so? Because we learned just Ashke that if there are two like charges, there's a point in between where the electric field strength is what? Zero. And when electric field strength is zero, what do we call this point? Null point. That's just so this is called the null point. Null point is a point where there is no net electric field, right? So tomadekke first of all to imagine korte hobe, how does a graph look like here? Can you tell me how does a graph look like? Yeah, it'll go from positive to negative, and as it goes from positive to negative, do you think it'll cross over at the center or somewhere on the other side? Right, so which way? Will it be closer? So my question, let's rephrase it. Is the null point closer to the plus 1.6 or closer to the plus 3.2? Okay, how many of you think is closer to the plus 1.6? Closer to the plus 1.6 and closer to the minus 3.2 rest of you. Okay, and one of you said middle. Acha, okay, so middle hobe na. Middle hobe kokhon if the charges were what? Equal, right? Now, the thing is, plus 1.6 is a weaker charge. To compensate for the higher strength of the other charge, you need to be further away from plus 1.6 or closer. Our repeat code to say plus 1.6 is a weak charge and plus 3.2 is a bigger charge. to equate and negate them, right? Do you need to be closer to plus 3.2 or closer to plus 1.6? Yeah, plus 1.6, because plus one, I'll give you a better example. The moon and the earth. Where is the null point between the moon and the earth? Closer to the earth or closer to the moon? Very close to the moon. And why is that so? Because moon's gravity is so weak that you have to go really close to the moon in order to just, oppose what the earth does, because earth is very strong, right? So you'll find that the null point is closer to this, and on the other side, it'll probably go like that somewhere. Okay, so that's how the graph is supposed to look like. But that's just speculation. Why? Because, we could be wrong. Do the math and tell me. So find for me what the null point is. That's the question. Sort of math kore proof koro if I'm right or wrong. Or proof bakira jara bolcho ora wrong. Find the null point. I'm going to detail this in null point location from the plus 1.6 into 10 to the power minus 19 coulomb charge. So yeah, where is it? The distance that you're trying to find is basically that distance, x. Null point, let's say. Zero 0.3. How did you do that? Don't guess it. .414. That sounds more appropriate. 0.3 to. That's what I was wondering. How do you get like a perfect fraction? 0.5 is much in it. How? Okay, let's solve this. Ashil, what do you do here? Yes. Yes. Which is, what did you do then? You basically equated the. That's okay. Yeah. And you got 0.414. That's okay. So Jara, I'm surprised and worried. This was there in the gravitational field topic. So at null point, what is the criteria? At null point, yes, net electric field strength. So electric field strength net E net is equal to 0. How do you find the electric field strength of this charge at that location? So electric field strength. So is this like a uniform charge or a non-uniform charge? Non-uniform, right? Non-uniform. I mean a non-uniform charge. It's a non-uniform field. So the formula for the electric field strength of a non-uniform field is E equals to KQ divided by D square. Okay, so that's going to be that. Now the whole thing is 1 meter and the left side is X, right? So what should this be? 1 minus X. What is the field strength of that going to be at this location? Also going to be based on what? E equals to KQ divided by D square. So at this point, the field strength of this plus the field strength of that must be equal to what? 0, because net is 0. Or you could do something else. This should be equal to that. because they're equal and opposite, right? But don't do both of them. Oneke ki korbe, they'll equate both of them and also take the sign. So answer double with it. So either you do this, okay? Take this as plus, take this as minus. So plus k cubed by d square minus k cubed by d square is equal to going to how much? 0. Or you can directly write k cubed by d square is equal to k cubed by d square. Don't put the sign here again. That way the thing gets complicated, okay? So the way I'll be doing this is at null point, that is 0. So the electric field strength of the plus 1.6 charge should be equal to the electric field strength of what? The plus 3.2 charge, right? So that's k 1.6 into 10 to the power minus 19 electric power. Now electrical problem now, because what happens eventually cancels out, right? So divided by x square equals to k into 3.2 into 1.6 into 10 to the power minus 19 divided by 1 minus x squared. এখানে একটা issue generate হয়, a math related problem, right? So if I solve this, the k cancels out, this cancels out, so you get 1 minus x divided by x whole squared is equal to how much? 3.2 divided by 1.6, right? The issue here is that whenever you take a root of a number, right, you get two outcomes. What are those? Plus and minus. That would actually give you two different values. So sometimes, right, you can have a null point inside and outside of a charge. And I'll explain that for a second. So how is it possible that there's a null point inside and there's a null point outside? So I'll give you an example. Imagine this is plus and this is minus, okay? And I have a positive charge here. What is this positive charge doing to the positive charge? Repelling. What is this negative charge doing to the positive charge? Attracting. Isn't it possible that they both can be equal and opposite, mathematically speaking? So it is actually possible to have a null point in unlike charges. Where does it lie though? Outside, okay? So the math will eventually show you that thing, so don't get surprised. It is possible, but probably nothing that they'll ask in the exam, okay? Just letting you know that the math sometimes will tell you that there's actually a null point, and then you might wonder, we learned there's no null point, right, in unlike charges. So they're talking about the null point outside. Anyways, এটা যদি solve করি, x কত আসে? 0.414 meters. So is it at the center or is it slightly skewed towards the positive charge here? It's towards that, right? So it's a little off center. Clear? Okay, so that's the first one. Just start the question. This one is find the net E for the positive charge. So you have a positive charge here, plus I'll give simple numbers, 4 coulomb. 4 coulomb, by the way, is a very large charge, because if you consider the charge of a single electron is 1.6 into 10 to the power minus 19, right? 4 is quite a lot of electrons out there. So this is plus 4 coulomb. And then you have another charge here at the bottom here. This is negatively charged. This is minus 10 coulomb. And you have your test positive charge here. Okay, plus find the electric. Yep. And distance is provided here. So this distance is equal to that distance, and that distance is provided. Okay, so isosceles. So yeah, so this is 5 centimeters, 5 centimeters, and it হচ্ছে 10 centimeters. Find the net field for this. Like এটার কতটুক strength experience করতে সেটা বের করো. That's it. তোমরা আমাকে এমনি বলতে পারো কি করবা? Net charge. What's net charge? Separately and subtract. You can add and subtract vectors under one condition. What is it? What is the only condition where you can add and subtract vectors? No. Yeah, they must be in the same line. Then only you can subtract and add. But if they're at an angle, you can subtract or add. What do you need to do? Vectors, diagrams, triangles, right? So in this case, you can't really add them or subtract them. Can we quit Korba? Acha, online, yes, what you said is right. You can resolve into components and find the answer, or Arjun to vector triangle create for it. That is also possible. Okay. Acha, আমি একটু বলে দেই কি করতে হবে এটা try করে আনবা মানে যারা আসবে এখানে তোমরা এখনই try করতে পারো. What you're supposed to do is this is a plus and this is a minus, right? What will they experience? Attraction or repulsion? Attraction. So there's going to be a vector this way. Okay. So let's draw that vector. And the other one, which is the plus and the plus, will experience what? Repulsion, which is going to be which way? That direction, right? So that is going to be another vector out there. You can find the values of these vectors. How? What is the formula for electric field strength for a non-uniform charge? E equals to K Q by D square. Our ওইটারটা কেমনে বের করবা? E equals to K Q divided by D square. And now you need to find out what are these two vectors. Resultant, right? To find the resultant, you can use either this method where you create a what? Parallelogram, right? Or you can take from here and place it there and can get that, which is called the vector triangle method. Or you could do something else, which is break this down into components and that, and then add the components, and that's how you find the answer, okay? So yeah, this is how you're supposed to do the question. Clear? না লাগবে না 10 সেন্টিমিটারটা আচ্ছা না 10 সেন্টিমিটার লাগবে কি আমাকে বলতে পারো 10 সেন্টিমিটার লাগবে yes you need to know what the angle here is green arrow is repulsion